Hi, welcome to the third of my presentation series on the conflict between science and creationism. Today's topic is astronomy, and as this is my own personal topic, I may go into more depth on this than on some of the others. As ever, the subjects I cover in this talk are those contained in the creationist presentations of Kent Hovind, the notorious young Earth creationist. If I were trying to cover astronomy from scratch, I'd probably do it very differently, but then again, I'd probably also take 20 times longer, so perhaps it's for the best. Astronomy is a huge subject, though just as with cosmology last time, it's got strictly nothing whatsoever to do with evolution. There are a few very big questions in astronomy that often arise in creationism discussions, and a whole host of smaller claims that are all pretty easy to disprove. Please also see Planetary Science, which will be a later talk, for some other related claims regarding the bodies in the solar system, and of course the second talk in this series in which I covered the subject of cosmology. Astronomy is, of course, not part of biology at all, and hence not part of the theory of evolution, though it is obviously of great relevance to creationism. If the entire universe was created 6,000 years ago, then practically all of science is wrong, and astronomy is certainly very wrong. So if young Earth creationism is right, then there cannot even be one object in the universe older than 6,000 years. In reality, it's very difficult to find anything that's anywhere near that young in space. The only way the creationists can get round this is by massive denial of the evidence and twisting of scientific theories. So let's get started. Astronomy is one of the oldest sciences that humankind has ever developed. Its name derives from the Greek word for star. Astronomy, after all, is the study of the stars. Most creationist claims in astronomy revolve around attempting to find ways to explain away the obvious antiquity of the universe by criticising the physics behind the way we take measurements, principally of stars, and the way we build theoretical models. For the universe to be less than 10,000 years old, there can't be anything in it that's older than this age, yet our models tell us that stars are very much older than this, and we know this from several sources. Star formation is an extremely well understood process. First of all, physical models show us how it should work in theory. Secondly, computational models demonstrate that this is feasible in practice. And thirdly, observations show us the various stages in this process happening all around us. The claim that we don't know how stars form is therefore nonsense. We can see star formation actually occurring at all stages by looking at various parts of our galaxy and nearby galaxies with powerful telescopes. We can see dense clouds of interstellar gas condensing into nodules which will eventually form star systems. We can also see those same nodules slightly further down the road, having condensed into protostellar disks, that is, disks of gas swirling around a central core which is gradually collapsing in on itself. As the core collapses more and more, it begins to get denser and heat up, until eventually the heat is high enough that nuclear fusion can begin in the core and a star is born. The remaining gas in the disk collapses into a flattened ring, and clumps begin to form, which form into planets. The light from the new star now begins to blow away the remaining dust, leaving a brand new planetary system. 4.6 billion years ago, this was happening to our own solar system, and it formed the Sun and all the planets orbiting it today. We also know a lot about star formation from theoretical models. There are two main types of models here: the n-body gas simulations, in which individual gas clumps are simulated collapsing in to form stars, or, at a larger scale, entire galaxies and even clusters of galaxies can be simulated using this method. There are also more mathematical simulations attempting to recreate the conditions inside a star, showing how it uses up its fuel, how the gases circulate, and how the energy moves from the inside to the outside, where it can finally escape the star as light waves to be observed in telescopes. Finally, in addition to all of this, there's plain old physics. We can calculate the timescales over which a star should burn simply by considering the nuclear fusion that's going on inside of it, working out its output in terms of light, and looking at how long it would take the Sun to burn up all its hydrogen given its current rate of burning. Again, these numbers come out in the billions of years. Over the next few slides I'll cover the process of star formation in more detail. This one's a bit technical, but it's important to understand. Momentum is a measure of the combined mass and velocity of an object. You can think of it as something like a measure of how hard it would be to stop an object from moving. So the more massive an object is, the more momentum it has, which means it would be harder to stop it. Think about trying to slow down a charging rhino versus a charging gerbil, even if they're both running at the same speed. But momentum also goes up as the speed goes up. If that rhino is running twice as quickly, then it will be much harder to stop, and it will do much more damage when it runs into anything. Angular momentum is almost identical to this linear momentum, except it deals with rotational motion. That is, it's directly related to how massive an object is, just like linear momentum, but it's also related to how fast an object is rotating. That could be an object spinning on its axis, like a spinning top, or it could be, for example, a planet orbiting a star. They all have angular momentum, which is, if you like, a measure of how hard it would be to stop it from spinning. This is something of a mystery, however, because in our solar system the Sun has almost all the mass. Something like 99% of the solar system's mass is in the Sun, and most of the remainder is in Jupiter. However, the Sun is spinning rather slowly. Despite having all that mass, its angular momentum is only about 2% of the total for the solar system. This seems strange. All other things being equal, the Sun should have a proportional amount of the angular momentum, and the fact it doesn't means that it's spinning very much more slowly than it ought to be. Why is that? Well, the answer in this case is simple. The Sun has simply transferred some of that angular momentum to the protoplanetary disk as the solar system was forming. Think of what happens when you spin a top and then place it in water or some other fluid. The top slows down because the water is dragging on it, and hence as the top slows down it transfers some rotational motion to the water, transferring the angular momentum as well. There are a few other issues with angular momentum that the creationists bring up. One of the highest profile issues is that the planet Venus seems to be spinning in the wrong direction. That is to say, if you look at all the other planets in the solar system, they're spinning on their axis anti-clockwise as you look down on them from above the disk of the solar system. Venus rotates the other way. How could that be? Surely they were all formed by the same disk spinning all in one direction. How could one planet spin the other way? Again, though the answer in this case isn't known for sure, the potential solutions are fairly simple. Something dramatic must have happened to Venus in the early days of the solar system, that's for sure. The two most likely events are that either it was knocked into a retrograde motion, that is, spinning in the opposite direction, by tidal forces in the protoplanetary disk, possibly caused by drag forces due to its thick atmosphere. Or perhaps more likely, some close interaction between Venus and another massive body, maybe one that has long since been ejected from the solar system, might have caused the slowdown and the change in direction. We know that such events happen. The Earth probably suffered one that formed the Moon. If the collision happened at the right angle, that could easily knock a planet into a backwards rotation. Interestingly, the gas giant Uranus is also in a similar state. Its axis of rotation is almost flat with respect to the plane of its orbit, which is again unique in the solar system. A large impact or close gravitational interaction is also proposed to explain this fact. Finally, another similar anomaly that is occasionally pointed out is that several moons of planets in the solar system spin in the opposite direction to the overwhelming majority of them. Similar explanations are proposed for this. Either they were subject to a collision after formation, or perhaps they were captured by the massive planet gravitationally later in their life instead of being formed alongside them, and the nature of their capture left them on retrograde orbits. What we've seen in this slide is a selection of examples of cherry-picking or anomaly hunting. What the creationists like to do is to sift through all the things they read in scientific theories until they come to one idea that's a little bit counterintuitive or doesn't seem to make sense to them immediately. With a bit of showmanship and spin, no pun intended, they sculpt a convincing story that seems to show that science is in trouble. Of course, a little bit of searching around usually turns up a perfectly acceptable explanation. If you want to find it, that is. If, however, you're happier with an explanation that an all-powerful, all-knowing God created the universe exactly as it is, with almost everything in perfect order but just a few things that were all wonky, then you're probably not going to look for a scientific explanation. Frankly, I find that a bit odd. We've sort of already met the stellar wind when I mentioned earlier how the Sun pushed away all the remaining gas in the solar system after the planets formed. There are actually two effects worth mentioning here, one of which is the solar wind and the other is radiation pressure. Radiation pressure is simply the pressure caused by photons, packets of light, ejected from the Sun and striking particles in space. As light has momentum, this effect is enough to push particles away from the Sun unless they're held strongly enough by gravity. Space agencies around the world are testing devices known as solar sails, which are exactly what they sound like, enormous thin membranes that can be released by satellites to take advantage of radiation pressure to propel spacecraft through space without need of an engine. The solar wind is related to this. It's a well-measured and extensively studied phenomenon that happens throughout the life of a star when tenuously attached charged particles in the outer layer of the star's atmosphere are ejected from the star and shot out into space at high velocity. It's believed that this is primarily caused by interaction of the charged particles with the solar magnetic field, acting as a sort of catapult. One objection that's been put forward to models of solar system formation is that the solar wind should have been so powerful in the early solar system that it should have pushed away all the gas before the planets even had time to form in the first place. This isn't really an objection because the creationists here haven't actually done the maths and simulations necessary to prove whether this is plausible or not. There are two forces at work here: pressure from the solar wind pushing particles outward and gravity pulling them in. And as soon as particles clump together in larger masses, then they become less and less affected by the solar wind. So it's just a question of whether this accumulation happened before the solar wind pushed out all the gas and dust. Looking at the vast numbers of extrasolar planets that scientists are now discovering in our galaxy, it's beginning to look like planets are pretty much ubiquitous around most stars, so that tends to hint that this process isn't much to worry about at all. A lot of what we're learning about star formation in theoretical models can be tested in reality by looking at solar systems actually forming using powerful telescopes. The two images on this slide, taken with the Hubble Space Telescope, are of the famous Eagle Nebula on the left and the Antennae galaxy on the right. The Eagle Nebula is a large cloud of gas and dust located 6,500 light-years away in the constellation of Serpens. The tower of gas you're seeing here is about 100 trillion kilometres high, or roughly 10 light-years. You may recognise this photo of the Eagle Nebula. The photo was taken in 1995 and appeared on the front covers of newspapers around the world, and it's been dubbed the famous Pillars of Creation. What you're seeing here are stars actually in the process of forming. You can see if you look very closely tiny nodules on the side of the clouds. These are protostellar systems which are just in the process of forming as the gas is collapsing under its own gravity. As you can also see, there are several stars in this image, many of which are actually associated with this cloud of gas. As a star forms, it begins to blow away the rest of the gas around it. On the right, the Antennae galaxy also give us an incredibly interesting insight into star formation. What you're actually seeing here isn't one single galaxy, but it's two galaxies that have recently collided. You can see throughout the image lots of dots of much brighter areas in blue and white. These are areas where the gas has been compressed by the force of the collision between the two galaxies, and this compression has triggered new waves of star formation. As you can see, astronomy shows us, not only through theoretical models but also through practical observations, exactly how star formation works. And this is a very well understood, as well as a strikingly beautiful process. Here are two more HST images to show star formation in action. On the left you see a small cluster of stars called the Pleiades. These are visible to the naked eye in the northern hemisphere, in the constellation of Taurus, and they're relatively close to our own Sun at a distance of just 440 light-years. These are mainly hot blue stars, as you can see from the image, which are very massive and relatively young. The stars you see are probably less than 100 million years old. You can still see plenty of dust in the cluster as well that hasn't yet been ejected from the system. On the right you can see a highly magnified image of an edge-on planetary disk, that is, a solar system in the process of forming. This one is in the Orion Nebula, which can be seen from both hemispheres. In the centre you can see the star, just beginning its life, with the disk of gas and dust coalescing around it. This gives us another data point when we're looking into how long a protoplanetary disk survives after the initial burst of nuclear fusion in the star. As you can see, the disk certainly isn't blown away immediately.